All right, section 10.1 concerns the topic of correlation, specifically linear correlation. And I'm going to talk a lot of vocabulary first, and then I'm going to talk some calculator stuff. Not necessarily stats yet, but calculator stuff. So, the notion of correlation. That is basically when one variable is somehow associated with another variable. Usually for us, X and Y. We like to say there is some correlation there if there is some relationship between the X that you pick and then the Y that comes out the other end. It doesn't have to be, oh, I don't know, in the sense of your algebra class, but somewhat similar to that, as you're going to see. We can use other variables, but usually it's X and it's Y. And there's really many different kinds of correlation. We are going to specifically focus on what we call linear correlation. Linear correlation, this is when the association between the X and the Y can be approximated with a straight line. All right, so that's what we're going to be working on today. Now, let me go ahead and just review a little bit about this notion of a straight line. I'm going to remind you of the notion of y equals mx plus b, where m is equal to the slope of a straight line and b is equal to the y-intercept. You'll remember graphing these kinds of lines in your algebra class. You would plot the b. This is the y-intercept, so the coordinate there is 0, b, and then you would walk off the slope. There was the notion of rise and run, and this would get you to a second point, and you could then graph the line. And there were other ways of going about doing it. Maybe you remember creating a table. It's another way of doing it. But I really want to remind people about this notion of y equals mx plus b, because this is what really we're going to work with here. We're going to focus on m, and we're going to focus on b eventually. But I want to get the review out of the way to begin with. So we're going to work a lot with this kind of model. Now, let me talk about the kind of data that we're going to use here. Bivariate is the name of the data. It's like, oh my God, what kind of crazy word is that? It really is the term we use, but bivariate data is just XY data. That's all it means. Bi because there's two, variate because there's two variables. So bivariate data, literally just X and Y data. And we'll be working with what we call scatter plots. That's where data consists of XY ordered pairs. We'll take a look at some examples in a few moments, but at the end of the day, it's really just a bunch of XY stuff, just like your algebra course was way back in the day. And a linear correlation just means that you have a cloud of data that is approximately, if you will, linear. It can be approximated by some sort of straight line. So when these data can be approximated by some sort of straight line, this is what we refer to as linear correlation. All right, now we talk a little bit more about correlation. Correlation can be essentially positive. It can be negative in the sense of the slope of a line. I'll remind you that a line such as this has a slope that is positive, and a line such as this has a slope that is negative. Some graphs have no real pattern at all. So you really can't fit a graph in there in any way, shape, or form. It doesn't look anywhere near line-like. Other data plots, or the other scatter plots, follow different patterns that you may remember from your algebra sequence of courses. For example, a parabola. Now, types of correlation, we like to measure the strength of this correlation with a value called R. Ooh, that's a crappy R. With a value called R. I'll talk more about R as I go along tonight, but in many cases, R can be positive, R can be negative, R can be close to 0, and the range of values of R falls somewhere between a positive one and a negative one. And I'll say that again in just a few moments, but you can find a value of R somewhere between a positive one and a negative one that talks a little bit about this notion of correlation. In fact, we have what we call the linear correlation coefficient. That's R. And this is the linear correlation coefficient for a sample. And what it does, it measures the strength of the correlation. Emphasis here on this notion of strength of the correlation. And R varies between -1, 0, and a +1. And I need a new sheet of paper to really get across how this goes. But in general, when we're at this end of the spectrum, the slope of my best line of best fit, as we like to call it, will be, whoa, not positive, is negative. At the other end of the spectrum, the slope is positive. In the middle, there is no generic slope, so we say there's little correlation. Now, let me show you how this value of R works. And it's important to remember that this works for a sample. If you have a situation where R is equal to -1, my graphs will have a negative slope, and they will look exactly like the graphs that you used to draw in your algebra class. The lines line up perfectly. M is equal to some sort of negative number. It's not the slope, let's be very clear on that. It just shows you how close to a perfect algebraic relationship it is. And when R is equal to -1, that's your perfect algebraic relationship with a negative slope. At the other end of the spectrum, it's R equals +1. The graphs out here graph from your algebra class with a positive slope, just like algebra. The lines line up perfectly. The points, I should say, line up perfectly along a line. So here, M is a positive value. In the middle here, at R equals 0, the graph has no pattern whatsoever we can discern. It is essentially cloud-like. That's where R is close to 0. At values between, say, R equals 0.7, you have a positive slope, but the points are somewhat scattered around that positive slope. If you have something like R is equal to a -0.3, you have a negative slope, but it's a bigger spread of data around that slope. So the tighter the spread of the data is, the closer that value gets towards either a +1 or a -1. If the data is relatively cloud-like, the R value will be close to 0. If it's relatively line-like, it'll be close to either a +1 or maybe a -1, depending on the positive or negative relationship. So that's how we think of R. And it's important to remember there is a different R for every type of relationship or type of correlation we wish to consider. That sounds complicated, but for us, it's not, because we only consider the R for a linear correlation. Now, there's a lot of notation involved, and I am going to steer entirely clear of the notation. And the reason for that is, well, the formula for R is really crazy. I'm going to put it in here once, but I want you to be very, very clear. I really expect students to use their calculator to find values like R and the other things that we'll actually really, really need. And then downstairs we'll have n times the sum of the squares of the x's minus the sum of the x's squared. That's all in a radical. Oh my God. And there's another radical downstairs also. Play the same game with the y's. But that equals, oh my God. But I'll show you some weird stuff once we get to our calculator. It looks really, really crazy. In the land of advanced statistics, this has some real utility, and it's not actually very hard to get to all those crazy numbers in there. So my calculator is really, really going to go ahead and help me with this. Now, what we're going to do next is we're going to take a look at our calculator and make sure our calculator can graph a scatter plot. So that's up next. Then we're going to get back to the statistics. But for the scatter plot for your TI-84, excuse me, I need some XY data. Let's see, make it a reasonably sized 6, 4, and -2, -1. What else? 1, 2, 3, 4. I want a couple more. -6 and -10. And the y values are going to go in the other direction. Let's see, they're going to go from a -3 to a -2 to a 1 to a 6 to a 4 to a 7. All right, I have no idea what that picture is going to look like. None at all. I'm going to go ahead. And by the way, there's already I think the technical term is buttload of exampled videos up in the Canvas course shelf. But here's one more for us to look at. All right. Oh, look at that. Someone must have been playing here. So you have to get your data into your calculator. You're going to need 2 lists. You haven't really needed 2 lists for quite a while, and never quite in this way. So 6, 4, -2, -1, -6, -10. And then over here in the land of the y, -3, -2. By the way, if you use the subtraction instead of the negative sign, you're going to get an error message at some point. All right, 1, 6, 4, and 7. So it's all in there. And by the way, when I ask you to work with these kinds of problems on quizzes and exams, the data sets are really somewhere around this size. I don't want it to become a button pushing race. So data sets are relatively reasonable. Now, I've got my data in there, and I really want to draw a scatter plot. Over here in blue, right above the y equals, is stat plot. So second, stat plot. Now, if you're going to try this at home, let's start from scratch. You're going to want to make sure all your plots are turned off. Otherwise, honestly, if you have competing plots, you can get some error messages, and it's confusing. So if you select plots off and hit enter, it says done, and everything is turned off there under the stat plot. Now you can start from a clean slate. Plot number 1, I will turn it on. I will scroll down to the type of graph. It's pretty self-evident, I think. The first graph looks very much like a scatter plot. By the way, if you have other graphs, you may very well have something completely different here. You need to remember you've got X and Y data. You're trying to draw something that looks suspiciously like that first little picture. And you indeed get, lo and behold, 2 lists, one for the X and one for the Y. Mark, just select the first one here, color blue. Now, at this point, and by the way, you can change the color if you want. You can even change the little mark, and I'll play with that in a moment. At this point, students may wish to select graph. If you do, that's okay. But I will note I got 1, 2, 3, 4 dots here. That graph had more than 4 dots. It had more like 6. So 6 data points, something's wrong. So clearly I didn't get the graph I wanted. So let me explain how to make that happen. You're all set to go. Don't run over here to graph. When you're doing a scatter plot, the most important key is under zoom. Zoom 9 is zoom stat. When I select zoom stat, my calculator will figure out the appropriate, I'm going to use words in a kind of an inappropriate fashion, domain and range. That is an appropriate list of X's and Y's that will give me the screen that I need to see my data. Remember, your screen is infinite. That's the plane. X and Y go into infinity in both directions. So if I select zoom stat, my calculator will pick for me appropriate parameters so I can see my data points. I've got all 6 of them here. Oh, look at this guy up here. He's crazy. In any case, that is how we draw a scatter plot. Once that data gets into my calculator in an X and a Y format, let me bring that down to not a 6, but I'm going to bring that down to a 2. Change that a little bit, just have something slightly different to look at. So once that data gets in there, you can go directly to second stat plot, select your list. And if you want, you can change the symbol that is used to identify the data points. Zoom 9 brings that up. I will point out something about the zoom stat. You really want to be able to see your picture. So some of these, where's red? Gosh, you're gone. There you are. Some of these are almost useless. There's a little teeny tiny dot. So now when I pick zoom 9, it's there, but I can't see it. So, take that under advisement. I like big, bold marks. Lets me see what I'm looking at. But there you go. You can pick different colors. You can even graph different sets. You've got 3 different graphs there, so you could work with that. So in any case, I'm going to leave that data in there because I'm going to come back to that data in just a bit. So let me stop my sharing for now. All right, so you saw in that particular type of scatter plot, so in that data we saw, and I'll use that adjusted data because that's the one I kind of want to use, and it was about something like that. And it was a pretty tight correlation. So for here, R will be close to -1. I have no idea what the equation of that line is. This is the line of best fit. That's also called the linear correlation equation. And I use the term line of best fit because there's a number of lines you might draw through that forest of data points, but one of them fits the best using something we call the least squares method. And I'll talk about that tomorrow, but not tonight. So the linear correlation equation gives us our line of best fit. This one will have an R value close to -1. Now, in this section, we test for linear correlation. So for example, a data set like that versus a data set like this, for example. This one here is much more linear than this one here. Nature's messy, never plays like your algebra class. So when we test for linear correlation, we test the claim that the population correlation coefficient is not 0. And to be really, really clear, we use the sample R to test claims about the population correlation coefficient rho. That's a Greek letter. So very much like we had X bar and mu, S and sigma, P hat and P, now we've got R and rho. You have your sample statistics, you have your population parameters. And for all tests, at least this semester, for all tests of linear correlation, we use rho equals 0 for the null hypothesis, and rho is not equal to 0. Rho equals 0 means no useful correlation. Rho not equal to 0 means we have a useful correlation. That means we can use X to predict Y. That's what it means. So if we are stuck with the null hypothesis, it means my graph is too cloud-like to be useful for X to be able to predict Y with any reasonable accuracy. If I'm rejecting the null hypothesis, then my correlation is useful, and I will, at least when I get to 10.2, be able to use X to predict Y. And let me lay out the details of this test, because this is where I really need to get to by the end of today. So, in a test for linear correlation, there are some requirements. And I'm going to let you really read the requirements yourself, but we need XY data. Basically, if the sample is really, really small, X and Y should both be approximately normal. And we need and this is what we really need, a visual inspection to assure an approximate linear relationship. See, this is where you take a look at the scatter plot and say, oh, yeah, it looks kind of like a little line a bit if I squint. But those are the real heavy duty requirements. And we have a test statistic and a t-distribution. I will not even bother to give you the test statistic, excuse me, because we're going to use a p-value approach. And we're going to use on your calculator on the TI-84, you're going to use, and I'll show you this in just a moment, something called lin-reg t-test. So on the TI-84, this is how we're going to test the claim rho equals 0, rho not equal to 0. All right, so let me track down that data. I'm going to put it back up here. And it's already in my calculator. So let me pull it out of my calculator. And then the last one, -10. All right, so that's the data that's in my calculator. We're going to assume all my requirements are met, and we're going to test the claim of linear correlation. This one, for whatever reason, can be a bit confusing sometimes for students to interpret, at least as far as the initial claim goes. So the claim of linear correlation means we're working with rho not equal to 0, which means I've got my alternative hypothesis. I'm going to use, for this problem, alpha equals 5%. That's my level of significance. So my data is already into my calculator. I'll be running over there in just a moment. So we're going to get going. Here's H1, rho equals 0. Sorry, H naught rho equals 0. And H1 rho is different from 0. Now I'm going to find my p-value and compare it to alpha. And then we can go on from there. And before I even show you the keystrokes, the really cool thing about this set of keystrokes is they're the exact set that you'll use in 10.2. And I'm going to have just a little bit of time, even if I have to go over to say just 1 or 2 words about 10.2 to help you on your way tonight. So let me go ahead and select my calculator. There you go. So you should be able to see list 1 and list 2. Remember where your data lives. We go all the way over to tests. Way down here, make sure you pick the right one, linear regression t-test. The X list is list 1. The Y list is list 2. Leave that alone. Down here, I'll talk about beta tomorrow, but this little guy here that looks like a jacked up P or Q or God knows what, that's rho. And we want to make sure we've got a two-tailed test. You leave that little guy blank and just hit calculate. You're going to get exactly the kind of thing you got from any sort of test in chapter 8. For the most part, you get a whole lot of other junk too. So there we go. So you've got a test statistic. You've got a p-value, 1.704 times 10 to the negative 4. That's the value I want. That's a tiny number. There's other stuff down here, and I'm going to come back to this in just a bit. Well, first off, I just went right on by it. There's R. That's that value of that gnarly equation that I showed you earlier. So the R value is there. Now, as I say, I'm going to come back to this in just a bit. Let me stop my sharing. So there's my p-value, 1.704. I guess I got one too many decimals in that rounding, but that's all right. I compare that to my alpha of 5%. So 1.704 times 10 to the negative 4th, 0.05. That's a tiny number. Remember, that moves this decimal four places to the left, making this teeny tiny. So we reject the null hypothesis. And we can then go ahead and say at alpha equals 5%, data, and by the way, if it wasn't clear, my initial claim was this guy right here, data support, rho not equal to 0. That really means I am justified in going on to section 10.2, which is what happens if we decide there's statistical evidence for correlation. All right, that's the test for linear correlation. It always runs the same. It's always a two-tailed test. You always have XY data. Yeah, sometimes they mess around with the claim here and the wording a little bit. But remember, this is the one that we really want to happen because it justifies using that correlation to make some sort of prediction. All right, so that takes me up through the end of 10.1. I have a little bit of time left, so I'm going to talk about 10.2. And I'll go over this in much more detail tomorrow, but I've got a little bit of time, and this will help you, I think, on your homework. So, section 10.2 as the title, regression. So once we have correlation, and we've got a nice, tight relationship, and we've rejected the null hypothesis, I want to know what the equation of that line is. Y equals mx plus b. Now, before I go any further with the 10.2 material, I want to just review a little bit more about our lines. So, and this is where I'm going to end tonight. Y equals mx plus b is what you know from your algebra class. Our book will use something different, and I'll explain the notation tomorrow. The book likes that particular form of the line, and it's a very common form of the line. And nothing has changed, but the roles have been changed. The slope is now the term with the slope is now the second term. So we'll have our slope is equal to b sub 1. The y-intercept, on the other hand, is usually listed first with a little b sub 0. So the y-intercept, b sub 0. So that is something to keep in mind. And it gets even worse than that. Your calculator likes y equals a plus bx. And here the relationship is more direct. Now, the really cool thing about this, let me jump back to my calculator one last time. When I did that linear regression t-test, at the top I have y equals a plus bx. Down below here, I have a and I have b. So from that example that we have, and I'll take a couple of decimal places, y is equal to 0.58. B, you see the negative there? I've got a negative slope, negative 0.62. So minus 0.62x. So that's the line that should best fit this data. In fact, if I plug that rounded version in, 0.58 minus 0.62x under the regular y equals key, that's the line of best fit. That's the linear correlation equation. Y equals 0.58 minus a 0.2x. So your calculator is quite capable of showing you everything you need to know. About the last thing I will say is the equation that we looked at when we were talking a little bit earlier tonight, and I referenced R. That's that one that had that really crazy number. You'll notice, by the way, that this number is close to a -1. That had that really crazy equation. Now, I'm going to remind you, this goes way back. Under VARs, under statistics, you see the little sum sign here? Your calculator has those x's, the x squares, the y squares, even the mixed ones. It's already summed up. So it's in some sense, it's really possible to get those values and plug them into an equation. You don't even need to look at them. You can plug them directly into an equation. Fortunately, my calculator does that for me every time I do the linear regression t-test. It goes and it calculates all those values. It even gives me the regression equation that I will need when I get to section 10.2 tomorrow night. So let me go ahead and stop my sharing. I'll talk a little bit more about this tomorrow. The last thing I want to say before I turn it off is take a look at the sections 10.1 and 10.2, like right away. If you look at the problems in 10.1 and in 10.2, they match up number by number for data sets. So the problem in 10.1 gives you XY data, say problem 10, 11, or 12, whatever it might be, gives you XY data, and they ask you to test for correlation. And then when you get to 10.2, that same problem number has the same data set. So usually what I tell students to do is to do 10.1 and 10.2 together. But that's kind of a stretch on a night like tonight. I'll talk a bit more about that tomorrow night, but I'm sure some of you are going to give that a try because it all comes out of that linear regression t-test. All right, I'm going to stop my recording.